How's that for an intro? Okay, today we're going to talk about the nucleus and radioactive decay. So first let's recall what an atom is made of. An atom contains a nucleus with orbiting electrons, and the nucleus is made up of protons and neutrons. If you recall, protons are positively charged and neutrons have no charge. Electrons that orbit the nucleus are negatively charged. There are three numbers that describe the composition of a nucleus that we will be discussing. The first one is the atomic number, which is denoted by the letter Z, and that indicates the number of protons in the nucleus. The second one is the neutron number, denoted by the letter N, and as you can guess, the neutron number signifies the number of neutrons in the nucleus. And lastly, the atomic mass number, denoted by the letter A, is the number of nucleons, so protons and neutrons, in the nucleus. So that's Z plus N. And if you recall, then the mass of an electron is really small compared to the mass of the nucleus, which is the proton and the neutron. So we don't really need to account for the electron mass in our atomic mass number. If you've ever checked out the periodic table of elements, you should be familiar with this specific format of representing elements. So the X here is your elemental symbol, so depending on what element you're looking at. Your A is your atomic mass number, so that is the weight of the entire proton, the nucleus, the protons and the neutrons combined. And then your Z, again, is your atomic number, and it's a number of protons, and that will determine where your element lies on the periodic table. So it's ordered sequentially. So as an example, how many neutrons are in the nucleus of a gold atom? So gold atom has the atomic mass number of 197. The elemental symbol for gold is Au. And 79 protons. So your atomic mass number is your number of neutrons plus your number of protons. And so if I want to figure out how many neutrons we have, it's just going to be your atomic mass number minus your atomic number, which in this case is 197 minus 79, and therefore we have 118 neutrons. Isotopes are forms of an element that have the same number of protons but different number of neutrons. Different isotopes have different levels of stability. There are certain combinations of numbers of protons and neutrons that work best and balance nucleic interactions. A stable nucleus will remain the same forever. An unstable nucleus can exist for a while but will eventually decay or break up. If a nucleus has more than 83 protons, so that's pretty big, there's no number of neutrons that will make the element stable. It's just so big that it's unstable and it's going to want to decay. Out with the old, in with the nucleus. Now let's talk about radiation. Radiation is the emission of energy in the form of electromagnetic waves or fast-moving particles. You've probably seen the electromagnetic spectrum before. If you notice, the lower frequency waves are located here, like radio and microwave infrared. Visible light is kind of in the middle, and that's light that we see. Ultraviolet, UV, X-ray, and gamma ray are high frequency waves, and the higher the frequency, the more energy it carries. So as we progress along this spectrum, we are increasing the temperature of atoms and molecules, and they all have a higher frequency as a result. There are three general kinds of radiation that we're going to be looking at. First is ionizing radiation, which are electromagnetic waves with enough energy to ionize or remove an electron from an atom or molecule. An example of this would be X-rays or gamma rays. The next type of radiation that we're going to be looking at is nuclear radiation, which is an ionizing radiation emitted from the nucleus, as the name suggests. So, unstable nuclei undergo radioactive decay and emit electromagnetic waves or fast-moving particles. Lastly, background radiation is radiation that can be found everywhere. So, these can be artificial or naturally occurring. Some examples are rocks or minerals that contain uranium or radon, bananas that I'm allergic to, or soil, rocks, water, air, vegetation, cosmic radiation are more examples. We're now going to look at 3 different types of radioactive decay. First one is alpha decay, and this type of radioactive decay involves a parent nucleus, which is your initial nucleus, that spontaneously decays into a daughter nucleus or nuclei, also known as a progeny. So this is a general form of an alpha decay. Your parent nucleus is the isotope that's going to be undergoing the decay. Before we talk about the daughter nucleus, I just wanted to talk about this, which is called the alpha particle. And the alpha particle is just a helium nucleus. Helium is the second element on the periodic table, has an atomic number of 2, and since it has 2 protons, 2 neutrons, an atomic mass of 4. So an alpha particle is a helium nucleus, and it's always going to be a byproduct of alpha decay. So therefore your daughter nucleus is going to be what's left over once you've separated the helium nucleus from your parent nucleus. So as you can see, your atomic mass is reduced by 4 and your atomic number is reduced by 2. So as an example, I'm going to do a really common alpha decay reaction, which is uranium-238 undergoing an alpha decay to become thorium-234. In this example, you'll notice both mass number and the atomic number are conserved. The mass number 238 on the left side and 234 plus 4 obviously adds up, and then 92, 90 and 2. Alpha decay typically occurs in heavier nuclei, so typically heavier than nickel. It's by far the most common form of cluster decay. It's the most common form because of the extremely high binding energy and relatively small mass of the alpha particle, which is a helium nucleus. Alpha particles are highly unstable and have a speed of about 15 million meters per second. That's about 5% of the speed of light. You wouldn't think so, but this is actually very slow. So, because of the relatively large mass and low velocity, alpha particles are likely to interact with other atoms and lose their energy. So they ionize other atoms, and so their forward motion can be stopped by a few centimeters of air. So they slow down pretty quickly. Here's a pictorial representation of our example. So parent nucleus of uranium-238 undergoes an alpha decay, emits an alpha particle, and the daughter nucleus of thorium-234. An element will undergo radioactive decay if it has more than 83 protons. So we're looking at the later portion of the periodic table. For a stable atom, the ratio of protons and neutrons is very close. So for example, carbon has 6 protons, 6 neutrons, so it's a very stable atom. On the other hand, something like bismuth, which is an unstable atom, has 126 neutrons and 83 protons. Also, nuclides containing certain numbers of protons or neutrons are more stable than others, and nuclides with even numbers of both protons and neutrons are more stable than those with odd numbers. Of course, there are exceptions to these rules. Beta decay is a type of radioactive decay in which a proton is transformed into a neutron, or vice versa, inside a nucleus. Because we're dealing with isotopes, this allows the atom to move closer to the optimal ratio of protons and neutrons, so it becomes more stable. As a result of this transformation, the nucleus emits a beta particle, which in this case is an electron or a positron. So we have two different types of beta decay, beta minus and beta plus. In a beta minus decay, a neutron is lost and a proton appears, and the process produces an electron and something called an electron antineutrino. For the sake of time, we're just going to look at beta minus decays. An example of a beta minus decay is thallium-208, and here it's undergoing a beta decay to release an electron. If you notice in looking at the atomic mass and the atomic number, this is a neutron-rich isotope. So there are a huge amount of neutrons in this isotope and fewer amount of protons. So it's highly unstable. The element wants to reach a more stable state. So it's going to release an electron and gain a proton. If you look on the periodic table, the 82nd element is lead. So our new element is lead, and we have our electron, which is released, as I said before, and our antineutrino. Now, an antineutrino has no charge. It's 1/10 of a million the mass of an electron, so very small, practically negligible in terms of mass, rarely interacts with matter. Beta particles, or electrons, travel at close to the speed of light, so much faster than an alpha particle. They can ionize, but due to the low mass, they're easily stopped. Often after a beta decay, the nucleus will also undergo an alpha decay. After a beta or alpha decay, the nucleons are in an excited state or disturbed arrangement, and they'll emit electromagnetic radiation. This is known as a gamma decay. In a gamma decay, the isotope isn't undergoing a transformation, but because it's unstable and you have an excited nucleus, which is denoted by that symbol, the electron moves to a lower atomic energy level and a photon is emitted. So a photon is a light particle that has no mass, no charge. It's just a high-frequency electromagnetic radiation particle. Because a gamma decay involves other decays, let's do an example of a beta decay followed by a gamma decay. So in this case, boron is undergoing a beta decay, where it emits an electron and an antineutrino, and we now have carbon in an excited state. The carbon in an excited state, the nucleus being in an excited state, is going to undergo a gamma decay, and so it will emit a gamma particle, which is a photon, and now we will have a more stable version of carbon as an end result. So here's a visual representation of a gamma decay. As you can see, we have an excited nucleus ready to undergo some decay. Now, as it decays, no change to protons or neutrons, except we do have a light gamma ray, a photon, being emitted. So just to do a comparison of the three types of radioactive decays in terms of their radioactive range, if we look at an alpha decay, as we remember, the helium nucleus is pretty heavy, so it's slow moving and it can be easily stopped. So it can be stopped by a sheet of paper. If we look at a beta decay, it can be stopped by sheet metal. It's a little bit faster, as we remember the beta particle is an electron, so it moves fast, can be stopped by maybe metal, and has maybe a longer range than alpha decay. Gamma decay, if we remember from the electromagnetic spectrum, has the highest frequency. So these are highly penetrating waves or particles and would need large amounts of dense mass like lead to stop it. When we're talking about half-life, we're referring to the amount of time required for something to fall to half its initial value. So we want to describe how quickly unstable atoms undergo radioactive decay, but it's also a term that's used for discussing any type of exponential decay. The decay of individual isotopes is nearly impossible to predict. We can more accurately predict when large amounts of an isotope will decay using the following equation. So here your A of T is your final amount after the substance has undergone radioactive decay. This is your initial amount. So how much substance you're starting off with. The half is basically your split factor. So after a half-life, 1 kilogram becomes half a kilogram. Little t up here is time, so how much time has elapsed, and h is your half-life. And h is equal to half of t, or t times half. Now, if you're looking for your final amount or your initial amount, and you have your half-life and your time that has elapsed, that's easy to do. You just plug it into the formula. If you are looking for your time or your half-life, you're going to have to use logarithms to get the exponent down. Okay, so now looking at this decay curve for iodine 131, you can see that the half-life is, since it's in days, is every 8 days. So every 8 days, you are left with half of what you originally started. So first 8 days, you have 50%. Next 8 days, 16 days later, you're down to 25%. 24 days later, you're down to 12.5% of what you originally had. And so it keeps decreasing in half. So as you can see, this is an exponential curve. And just to give you some perspective, uranium-238 has a half-life of 4.5 billion years. So 1 kilogram of uranium emits 3 million alpha particles per second. So you're getting a lot of value there. Thanks for hanging in. Here's your outro.